Ever wondered why an apple doesn't fly upwards when it falls from a tree? Or why you feel a push forward when a car suddenly stops? Newton's laws can explain these phenomena. Welcome to the bedrock of physics, the foundation of how we understand the world around us. These are the laws that Sir Isaac Newton formulated centuries ago, yet they remain as relevant today as they were back then. Newton's laws of motion, three simple yet profound principles that govern the movement and interaction of all objects. In the scenes to come, we'll be delving into each of these laws in detail. We'll start with the law of inertia and then move on to the law of acceleration. Lastly, we'll explore the law of action and reaction. So buckle up as we dive into the intriguing world of Newton's laws. Imagine you're on a frictionless ice rink. What happens when you push off from the side? You keep sliding, right? That's the essence of Newton's first law. Let's break that down a bit. Sir Isaac Newton, a brilliant mind of the 17th century, gave us three laws of motion. The first of these is often referred to as the law of inertia. But what does that mean? Well, in the simplest of terms, Newton's first law states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an unbalanced force. This might sound a bit technical, so let's use a few everyday examples to illustrate this law. Consider a soccer ball lying on a field. It's at rest, right? It's not going anywhere unless someone or something applies a force to it. Maybe the wind picks up or a player comes along and gives it a good kick. That force will set the ball in motion. But what happens if no one touches the soccer ball? It stays right where it is. Why? Because there's no unbalanced force acting on it to change its state of rest. That, my friends, is the law of inertia in action. Now let's say that ball is already in motion, soaring through the air after a powerful kick. According to Newton's first law, it'll keep moving in the same direction and at the same speed unless an unbalanced force acts on it. Maybe that force is gravity pulling it back down or a goalie swooping in to make a save. But without that force, the ball would keep on flying. The same principle applies to you on that imaginary ice rink. Once you push off, you'll keep sliding along until something stops you. Maybe you hit the side of the rink, or perhaps friction eventually slows you down. In other words, objects love to do what they're already doing, and they resist change in their state of motion. That's inertia for you. Ever noticed how harder you have to push a heavy shopping cart compared to a light one? That's Newton's second law at play. Let's delve into this law, also known as the law of acceleration. Isaac Newton, the genius behind these laws, stated that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Sounds a bit complex, doesn't it? But don't worry, we'll break it down. Think of it like this. You're trying to move two things, a bicycle and a car. Both are stationary and you have to apply force to make them move. Now, which do you think will move more easily? The bicycle, right? And that's because it's lighter than the car. This is where Newton's second law comes in. It tells us that the acceleration, or how quickly something speeds up, depends on two things: the force you apply and the mass of the object. The more force you apply, the more the object accelerates, but the heavier the object, the less it accelerates. So, let's go back to our example. You push the bicycle and it easily accelerates because it's light. But when you push the car, it doesn't move as easily. That's because it's heavy, so it needs more force to accelerate. But what if you apply the same force to both the bicycle and the car? The bicycle will accelerate faster than the car. This is because acceleration is inversely proportional to the mass of the object. The lighter the object, the faster it accelerates when a certain force is applied. In essence, the law of acceleration is a principle of motion that explains why heavier objects require more force to move, and why lighter objects move more easily with the same amount of force. It's the reason why pushing a shopping cart full of groceries is harder than pushing an empty one. So, the heavier the object, the more force you need to change its motion. That's the law of acceleration for you. Why does a gun recoil when fired? Or why do you move backward when you jump off a boat? Welcome to Newton's third law. This principle of motion is all about action and reaction, and it simply states that for every action, there is an equal and opposite reaction. Now, this might sound a little abstract, so let's break it down with some everyday examples. Imagine you're a swimmer at the edge of a pool. You push off the wall with your feet, and suddenly, you find yourself gliding through the water. But have you ever wondered why? Well, as you exert force on the wall, the wall exerts an equal force back on you. Your action of pushing against the wall creates a reaction, the wall pushing back. This reaction is what propels you forward. Or let's take the example of a rocket launching into space. When fuel is burned, gases are expelled downwards from the rocket. This is the action. The reaction is the upward thrust that lifts the rocket into the sky. The force of the gases going down is matched by an equal force propelling the rocket up. And how about the humble act of walking? When you walk, your foot pushes against the ground, and the ground pushes back with an equal force. This reaction force is what allows you to move forward. So you see, Newton's third law is at play all around us and in ways we might not immediately recognize. It's in the recoil of a gun, the leap of a frog, the flight of a bird, and even the rotation of the Earth around the sun. And remember, this law is universal, applying to all objects and particles in all realms of the universe, from the tiniest atoms to the most massive stars. So every action indeed has an equal and opposite reaction. That's Newton's third law for you. So we've been on a journey through Newton's laws of motion. Let's take a moment to recap. Firstly, we dived into Newton's first law, also known as the law of inertia. This law states that an object at rest stays at rest and an object in motion stays in motion, unless acted upon by an external force. In other words, objects resist changes in their state of motion. Imagine you're cruising along in your car with the windows down, and suddenly you hit the brakes. You lurch forward, right? That's your body resisting the change in motion, a practical demonstration of the law of inertia. Next, we explored Newton's second law, which deals with the relationship between force, mass, and acceleration. It posits that the force exerted on an object is equal to the mass of that object times its acceleration. In simpler terms, if you push a heavy object, it will accelerate less than a light one with the same force. Consider a small pebble and a large boulder. You can easily kick the pebble and send it flying, but the boulder, not so much. That's Newton's second law at work. Finally, we examined Newton's third law, the law of action and reaction. This law asserts that for every action there is an equal and opposite reaction. Think about jumping off a diving board. As you push down on the board, action, it springs you upwards into the air, reaction. Throughout our lives, we experience these laws in action, often without even realizing it. They govern everything from the smallest particles to the largest celestial bodies, making sense of the physical world around us. And there you have it, the world around us explained by Newton's laws. So next time you see an apple fall from a tree, you'll know there's more to it than meets the eye.